Welcome to the Deep Dive. We're the place where we take, those really compelling sources and dig deep to pull out the knowledge nuggets you need to be truly well-informed. Today, we're plunging into a document that, frankly, challenges some of the most fundamental ideas in modern physics. In cosmology, even. Get ready to have your mind maybe stretched a bit. The document we have here, it's called Everything.pdf by Michael Scott Peck. And it's not just a paper, it's presented as a theory of everything. It offers significant corrections to general relativity and puts forward a totally new, continuous model of the universe. That's a pretty big claim.
It really is. And what's fascinating here, I think, is the approach. This work presents a kind of conceptual inverse to a lot of our current understanding. It suggests solutions to these really big cosmological problems might actually come from reevaluating some foundational assumptions we've, well, maybe taken for granted.
Right. So our mission for you, the listener, is to unpack these truly audacious ideas. We'll explore how this theory redefines particles, space-time, the universe's origin, its fate. It offers some surprising claims and definitely a whole new perspective. So let's dive in. First big piece, the vacuum field theory. Okay, so let's unpack this. Many of us know Einstein's general relativity, right?
Yeah.
And it often treats particles, electrons, protons as these tiny point-like sources, little dots almost. But this document, Peck's work, it completely turns that on its head.
Right.
What's the fundamental shift here?
Exactly. Peck argues particles aren't points at all. They exist as localized fields. Think of them less like a tiny ball, more like a persistent concentrated ripple. A stable disturbance in the vacuum itself. And here's where it gets really different. These aren't just math tricks. They're actual vacuum fields undergoing transformations. But, and this is key, they remain locally invariant with respect to the space-time metric.
Okay, locally invariant with respect to the space-time metric. That sounds technical. Can you break that down? What does it mean for space-time itself?
Sure. Think of it like this. Normally, we picture space-time as the stage, and particles act on it, warping it. Peck flips that. He suggests the space-time metric, how we measure distance and time, actually encodes the shape, the deformations of these localized fields.
So space-time isn't the stage. It's more like the record of the actor's movements.
Kind of, yeah. It's as if space-time is the description of these fields rather than the fields influencing some separate external thing. Space-time is woven into the fields themselves.
Wow. Okay, if particles are fields, not points, that's a huge shift. So what does that mean for the really extreme stuff, like black holes or gravitational waves?
Right. This brings up a really important question. The paper draws a direct line between things like event horizons and gravitational waves as they pop out of Einstein's field equations, the EFEs, and using those point-like sources in the math. With this vacuum field theory, Peck argues, it demonstrates that event horizons can no longer form without infinite classical energy.
Infinite energy.
Which is impossible, right? Physically impossible. So the implication is stark. Event horizons, as predicted by GR, simply don't exist in reality, according to this model.
Wait, hold on. The event horizon, the point of no return, that's gone.
That's a massive claim.
So what is a black hole in Peck's universe? Still there, but different?
Exactly. No cosmic one-way door. Black holes would still be incredibly dense, incredibly powerful objects, but they'd be finite black holes. Their surfaces would have a finite vacuum energy density. They'd still have strong external fields. They'd still emit nearly perfect black body spectrums. And energy would escape, not just through relativistic jets, which we see, but also through something called free field radiation.
So they're still black, still powerful, but leaky. No singularity, no absolute edge.
That's the idea. Dynamic, finite, but no absolute trap. It completely redefines them.
That's quite something to picture. Okay, so black holes are different. Does this theory also change how we think about space and time themselves? You mentioned the metric.
Absolutely. It challenges the mainstream view, the idea of space-time as this unified physical four-dimensional thing, this manifold. Peck's view. Space and time should instead be treated as two independent entities. Space is, well, space. A classical manifold, the physical room we're in, essentially. But time. Time is different. It's a manifestation of relativity or event comparison.
Event comparison. So time isn't like a river flowing. It's more like ticking off events.
You could think of it that way. It's more abstract. Time is a scalar quantity, the paper says, that depicts change in abstract variables. It's how we measure change, not a dimension you travel through. Theoretically, it could become undefined where you have infinite vacuum energy density, but again, that needs impossible infinite energy.
Got it. So for you, the listener, this isn't just tweaking physics. It's rethinking the fundamental canvas. Time is a measurement, not a dimension. That's profound. Okay, so if particles, space, and time need this kind of overhaul, wow, imagine what that does to the biggest story we tell ourselves. The Big Bang. This paper pulls no punches there.
No, it really doesn't. The paper argues very strongly that ACDM, that's the standard model, lambda-cold dark matter is, and I quote, conclusively ruled out. It points to anomalies, unexplained observations, and various non-classical assumptions baked into the standard model.
Like dark energy.
Like dark energy, yeah, which the paper notes cannot be directly detected and argues is not predicted by the standard model, but was added later to make things fit.
So if CDM is out, what about the evidence for it? Like the universe's accelerated expansion. Is Peck saying that's just wrong? An illusion?
Precisely, an illusion. He argues it's due to local geodesics deflecting towards the center of an asymptotically flat linear universe.
Whoa, okay, so light paths bending make it look like things are accelerating away. But the universe isn't actually expanding like that.
That's the core idea. Light from distant objects bends towards a central point in this different kind of universe structure, creating the redshift we interpret as acceleration. So, no need for dark energy to explain it.
That's bold, especially with all the data pointing to expansion. But Peck must have specific observations he thinks contradict ACDM, right? You mentioned anomalies, like the faint blue galaxy problem.
Yes, that's presented as key evidence. The paper cites this problem where the standard ECDM model is apparently off in galactic number densities, and it underestimates their size by 200–500%. These faint blue galaxies look similar to galaxies nearby, but CDM predicts they should be much smaller way back then. Peck claims this leads to systematic lensing errors.
Misinterpreting distances and sizes because the underlying model is wrong.
That's the argument. And another major disagreement is about galactic evolution. This really flips our timeline upside down.
So, well, CDM says distant galaxies seen far back in time should be younger, less evolved. Makes sense, right?
Yeah, standard picture. But Peck's continuous model predicts the opposite. They should be older than local populations. He points to things like observations of galaxies cooling with increasing redshift, higher metal content like higher Fe.MGI ratios in distant quasars, which suggests more processing, more age, and even things like the infall velocity of the bullet cluster apparently don't fit CDM predictions well.
Older distant galaxies. How much older are we talking?
Dramatically older.
Yeah.
The paper gives an example. Some distant objects at redshift 8 are observed to be approximately 140 billion years older than the local group.
140 billion years older, when the standard model says the whole universe is only about 13.8 billion years old.
Exactly. It's a massive discrepancy, obviously incompatible with the standard timeline.
Okay, so if the Big Bang is out, expansion is an illusion, and distant galaxies are older. What's the alternative picture? What is Peck's universe?
The alternative is this continuous model of the universe. It proposes an asymptotically flat linear universe. Imagine it not expanding, but having a large-scale structure, maybe like a vast plane with a central core. Redshift, then, isn't just expansion. It's a mix of relative motion and gravitational potential within this structure.
A central core. Okay, but what about the cosmic microwave background, the CMBR, that afterglow of the Big Bang? How does that fit if there was no Big Bang?
Yes. The CMBR, this is where the model gets really creative. Instead of a Big Bang relic, the CMBR is proposed to be classical black body radiation emitted from the central core. Think of the core like a massive distant radiator glowing at about 3000 K before redshift stretches the light. And it has to be huge, more massive than any local object to produce that glow. The paper contrasts this with the tiny mass Hawking radiation predicts for a 3000 K Einstein black hole, calling this direct proof against the existence of event horizon.
So the CMBR comes from the center, not from everywhere, right after the beginning.
That's the claim. And this model also claims to explain the dark flow, that weird, large-scale motion of galaxy clusters all seeming to head in one direction. Simple. They're continuously flowing towards the center of the universe, towards that massive core.
But wouldn't everything just pile up?
But it's a cycle. Matter falls into the core, yes, but then relativistic jets emanating from black holes at the core's poles shoot dense quark matter back out. There's even speculation about a strange quark-anti quark layer at the core that separates matter and antimatter, creating an abundance of protons and electrons in our hemisphere and antimatter in the other. This is suggested as a solution to baryon asymmetry.
Baryon asymmetry, why we see matter, not antimatter. So it's like a cosmic recycling plant, a perpetual machine universe.
Effectively, yes. That's a good way to put it. It operates in an anisotropic state of entropy. Entropy isn't just uniformly increasing, it's balanced. Entropy is constant for all time relative to the preferred reference frame of the core. It's a steady state, constantly recycling, constantly reorganizing, maintaining itself without violating thermodynamics, no beginning, no end, just this grand cycle.
Okay, let's circle back to something we touched on earlier, gravitational waves. The paper takes aim at those too, doesn't it? Another pillar of modern cosmology, potentially knocked down.
Yes, it's quite direct. The existence of gravitational waves is crucial to the validity of EFEs, the Einstein field equations. That link is clear. However, if particles are these localized fields, not the point sources the EFEs often assume for these calculations, then the theoretical basis for GR's version of gravitational waves is undermined. The paper mentions the current probability of non-existence and points to highly variable theoretical event rates for detecting them, suggesting that doubts are warranted even with the detections we've had. It questions what exactly is being detected.
Interesting. So the detections might be real, but maybe not the space-time ripples predicted by standard GR.
That seems to be the implication explored. And then there's dark matter, the invisible stuff supposedly holding galaxies together. Does the continuous model need it?
Let me guess.
No.
Not at all. In this framework, dark matter is seen as a kind of theoretical artifact, a consequence of using the wrong model, ACDM. The paper argues that the evidence for dark matter, things like gravitational lensing from distant clusters or those unstable rotational curves of galaxies, is actually due to systematic lensing errors.
Errors again. Stemming from what?
Stemming from ACDM having the incorrect shape of the universe and using improper foundations like the virial theorem to estimate mass in the first place. Basically, if your cosmic map and measuring tools are wrong, you'll infer things that aren't there.
Okay, but what about really strong evidence, like the bullet cluster, where normal matter and inferred dark matter seem separated? That's often called the smoking gun for dark matter. Right. The paper addresses observations like the train wreck cluster and the bullet cluster. It claims that where we see lumps of dark matter coincide with both galaxies and ICM, the hot gas between galaxies, this isn't proof of dark matter. Instead, it's presented as strong evidence for systematic lensing errors inherent in the standard model's interpretation.
So even the bullet cluster is reinterpreted as a mistake in our calculations.
That's the assertion. Plus, remember those vastly longer timescales in the continuous model. If local space is potentially over 100 billion years more than ZCDM's age, you simply don't need dark matter to pull things together quickly to form the galaxies and structures we see. Time does the job.
Wow. Okay. You've just taken us on a deep dive into a truly revolutionary perspective on the cosmos, from the very nature of particles, redefining them as fields, all the way up to the structure and history, or lack thereof, of the entire universe. Michael Squonpeck's theory really does challenge almost everything.
It really forces you to step back and question the foundations, doesn't it? It poses this fundamental question. What if the universe isn't expanding? What if it's this vast, steady state system? A system with a central core, recycling matter, where things like event horizons and dark matter, concepts we've grappled with for ages, just aren't real. The paper makes the bold claim that its model, using only classical assumptions, actually agrees with all observations, while the expanding universe model is conclusively ruled out. It's a stark contrast.
So for you, the learner, this deep dive has certainly broadened our horizons, maybe even bent them a little. We've encountered some genuinely surprising ideas. Particles as fields, black holes without inescapable edges, a universe recycling itself forever instead of starting with a bang. It's really an invitation to consider an alternative narrative. What if our fundamental picture of reality, from the tiny quantum level to the largest cosmic structures, needs more than just tweaking? What if it needs a complete rethink? Could simplicity and classical ideas, rather than adding complexity like dark energy or dark matter, actually hold the key? This definitely gives us a lot to think about, maybe even changes how we look up at the night sky next time.
If you like the video, please like and subscribe. Also, don't forget to share the video.